This is the video for the second part of 4.2 or 3.2 in the 6th edition. We're talking about the zeros of a polynomial function. So we're going to be talking about graphs of polynomial functions, and before we really get started, let me just say that we know that the equation of a polynomial has all whole number exponents, right? And we know that the domain is all real numbers. The other thing we should know about a polynomial function is that it's a smooth and continuous function. So it might look like this, right? It would not look like this. Okay, there will be no sharp points. So this sharp point right here would mean this is not a polynomial function. Okay, it would also not look like this, where it's not continuous, where there's a jump. Okay, that would not be a polynomial function. It's a smooth and continuous function. So here's a polynomial function, and what we want to talk about are these places right here where the function equals 0. Okay? If the function equals 0, then that place, that point on the x-axis, that's called a zero of the function. So it crosses here at 1, so 1 is a zero of this function. And -1 is a 0, and -2 is a 0. And you notice there are 3. This happens to be a third degree polynomial, and the most it could have are 3. Now, we have other names for these. We've also called them x-intercepts, right? So as long as our zeros are real numbers, then the x-intercept is exactly the same as the real number. And think about how we used to find, in the past, we've found zeros, mostly for quadratics, but we did a few cubics, and we found them when we were able to factor. So I have this equation written here, all factored, and you see that the factors are x minus 1, which means 1 is a 0. So see, there's a 0 here at 1, so 1 factor is x minus 1. 1 factor is x plus 2, which would mean there's a -2 that's a 0, right? Because at -2, this would equal 0. And x plus 1 is a factor, so that means -1 is a 0. Okay, so having a factor will tell us the zeros, and if we know the zeros, then we know the factors. So there really are like 4 ways to say this. Okay, so if we know that C is a 0 of some polynomial, right? I'll call it P, we'll call it P of x, that's our polynomial. Okay, that's the same thing as saying that if I plugged in C, it would equal 0, right? So if I plug in the 0, that means my answer was 0. It's also the same thing as saying that C is an x-intercept. Okay? It's also the same thing as saying x minus C is a factor of P of x. Okay, those things are all the same. It's all saying the same thing. And we can use them, whichever ones we know or whichever ones we need to know. We can go back and forth. If we know something about C, that means we know the other things about C. So one thing that we can do is we could come up with the polynomial. So suppose I know that there's a polynomial and the zeros are 1, 2, and 5. Could I write an equation that had those zeros 1, 2, and 5? Well, I could, because remember, if something is a 0, then x minus that number is a factor. So my polynomial, I'll call it p of x, I know it's going to have a factor of x minus 1, it's going to have a factor of x minus 2, and it's going to have a factor of x minus 5. Okay? Now, there could be a number out here in front, right? And I could stretch it or I could shrink it, but basically those are the only factors if I know it's a third degree polynomial, right? But those would be the only factors if those are the only zeros. What that means, the a out here, what that means is if I have if I have something that looks like this, that would be a polynomial that goes through those zeros. If I have something that looks like this, that would be a polynomial that goes through zeros, those 3 zeros. Or I could switch it around this way, right? And all that would just depend on what that a is. Right. Let's just let a be 1 for a minute, and let's think about this polynomial and what we know about its graph. Okay, so basically, here are my zeros again, right? 1, 2, and 5. What I want to look at is what do I know about this interval? So if my only zeros are 1, 2, and 5, then that means that's the only place it crosses. And if one number in that interval is positive, then they're all positive. And if one number is negative, then they're all negative. Because for it to go from positive to negative, for it to switch around, it would have to cross the x-axis again, and it doesn't. It only crosses at these 3 places. And that's actually a really important theorem. They call it the intermediate value theorem, where we know that if there's one place where the function is positive and there's one place where the function is negative, and remember the polynomial functions are continuous and smooth, they don't jump around, we know that it has to have gone from positive to negative, it had to cross 0. There's no other way to go from positive to negative unless it crossed 0. So we do know that these are all going to be the same. If they're positive, they're all positive. If they're negative, they're all negative. And let's look what happens. Let's plug in, let's say, 0. Then I'd have negative, negative, negative. So 3 negatives, that makes a negative. So everything in that interval is negative. All right, so now let's look at this interval. The interval between 1 and 2. So like if we take 1.5, well 1.5 minus 1, that's still positive. But these would both still be negative, so that would make us positive. We've got 2 negatives multiplied, that makes a positive. And then we would look at the next interval. And it's going to be a negative, and this can be a positive. You already knew that it was going to alternate, right? So as long as there's nothing weird, there's no duplicates or anything like that, we can let it alternate. But if you have any doubts at all, then check every one. And if 2 of those are the same, if 2 of the factors are the same, then you have to check every one, because it will be different. So what we know is that coming up here from negative infinity, it's going to cross right here, but everywhere it's going to be negative until it gets to 1. Then it's going to be positive, and we don't really know whether it's a big loop or a big tall one or really close to 0, but it's positive. And then it's negative in the next interval, right? And then it's positive. You can only assume it's going to alternate if all the factors are linear factors. That means they can factor all the way down to x plus or minus some number, and there are no duplicates. Okay. Now, how far does it come up right here on these loops? I don't know. We could plug in a point and we could find out. But most of the time, I'm more interested in just, in general, how it looks. Here's one of the things I want you to notice. If I multiplied this all out, it would be a third degree polynomial, right? The very first term would be x cubed. And you notice that just like our x cubed, just like our x cubed function from our library of functions, remember, the end behavior, like we talked about in the last video, is that it goes up to infinity as x goes to infinity. It goes down to infinity as x goes to negative infinity. Okay, now I want you to also notice that right here there is a local maximum, and right here there's a local minimum. So it's possible for us to have at most 2 of those if we have a third degree polynomial. So why would that be? Well, with a third degree polynomial, we have 3 zeros at the most, right? We couldn't have 4, because if we had a fourth one, we would have to have a fourth factor, and that would mean it would multiply out to be a 4th degree. So the most we can have are 3 zeros, and those maximums and minimums have to come in between zeros. So the most maximums and minimums we could have are 2. It's always going to be 1 less than the degree. Now, do we have to have 2? Well, no. Look at this one over here. We just drew the x cubed. It's third degree. There are none. So we could have less than 2, but we can't have more than 2. Okay, so we'll do some more graphing of these polynomials in the next video, but the most important thing for you to remember from this one is that the 0 matches up with the factor. So if you can factor, you can find the zeros. If you have the zeros, you can find the factors. Okay, here is your quiz question. I want you to find all the real zeros of this polynomial, and we would find that by, here's your hint, by factoring, and you can factor this by grouping. You start by grouping and make sure you keep going until you have it all the way down to linear factors. You should find 3 of them. Put those in the quiz, enter them as a list separated by commas. Don't put any spaces in, and then your answer should be there. All right.